Yeah. Good morning, everyone. Hello. Is I'm audible, right?
Yes, sir.
Hello. Welcome back, all of you, to the day five. The lecture will be on fundamentals of mathematical optimization, microgrid, and effects of penetrating microgrids with storage on conventional grids. Yeah, Professor, you can go ahead of starting the lecture.
Okay, good. Good morning, everyone. Welcome back to the Gian course. So this lecture is my last for the whole course. So the topic is on the microgrids. So first of all, I will introduce some fundamentals of the mathematical optimization, which will be applied for microgrid energy management. And after that, I will introduce some basic concepts, infrastructure of the microgrid. And after that, I will show you some specific research works on microgrid optimization with energy storage. And you will see how this microgrid can exchange the power with the conventional main grid for during its operation when it is trying to maximizing its revenue. And so that is basically the topic of today. So three sessions. First of all, we will quickly go through some principles for mathematical optimization. I suppose many of the participants are already familiar with that, but we will still have a quick overview, including the mathematical model, like a mathematical property of optimization model, so on and so forth. And after that, the second session, I will introduce the economic dispatch and optimal power flow model, which are basic tools for power system operation. And this one will certainly be used by microgrid operation as well. And in the third part, as I just said, I will show some two actually examples for the microgrid with energy storage to optimally operating with power exchange with the main grid. Specifically, I will illustrate a case for the hybrid energy storage system in the microgrid. Remember, in the previous lecture when we introduced energy storage technology, right? One of the case is to combine different energy storage technology to leverage their advantages simultaneously. So later on, I will give you such a case which combines supercapacitor and lithium batteries together to for the power dispatch. Okay. Now, talking about the mathematical optimization, first of all, we need to understand the definition of the optimization. Okay, I suppose this terminology is frequently used in, either technical settings or in our daily life, because sometimes we want to find a best. We want to find a best solution. We want to find a best answer or a best choice, because in our daily life we have numerous choices. We have numerous options. So of course, we want to find a best. So optimization is actually to find a best solution of a problem. Now the next question is, how do you define the best? Okay, different people, they may have different preference, and they have different criteria. So how can we define the best? Now, in mathematical context, the best means the minimal or the maximum value of an objective function. So first of all, we need to have an objective, right? For example, our objective is to find the best course to study. Okay, we want to find the best clothes to wear today, right? So we have to define such an objective. Then mathematically, this objectively should be modeled in the kind of algebraic format. Then the minimum or the maximum value of this objective function is called the best, right? And the solution of the best is also called optima in mathematical terminology. Now, when we talk about the optima, mathematically, they can be generally classified into local optima and global optima. Okay, by its name, local optima means the optima near in a kind of local searching region, while the global optima means the optima value of the entire solution region globally. Okay, now let me quickly show a case to help you to understand the difference between local optima and the global optima. Now, if we have a kind of quadratic function and our objective is to find the minimum value, okay, of this quadratic function. So clearly you can see this is the optimal solution of this problem, right? Because our objective is to find the minimum value of this quadratic function. So you can see that this is the optima in this kind of solution region shown in the screen, right? This is the minimum value within the whole solution region. So in this case, this is a global optima, right? This is a global optima. And however, in sometimes the objective function could be more complex. For example, now the objective function becomes such a kind of a complex curve, which is like a sinusoid waveform. And our objective is still to find the minimum value of this objective function. Now, clearly, everybody can understand the minimum value of the entire objective function will be the blue point, right? So this blue point is the so-called global optima because this is the least minimum value that we can find in the whole solution region. However, you can see we still have some other small values like these two red points. You can see that these two red points, they are still optimal value near within the nearby neighboring region, right? For this red point, it is the minimum value within this region, and this red point is the minimum value within this region. However, the true global optima is the one here. Okay, so these two red points are called local optima because they are optima just within the local region near this kind of solution region. But the blue point is so-called global optima. Okay, so of course, when we solve optimization model, we want to get the global optima because that is the minimum, maximum value of the entire problem. But sometimes, given a very complex problem, it's very difficult to search the global optima because one of the straightforward approach to solve a optimization problem is to use its gradient. Okay, everybody knows that we can, in order to find a kind of optimal value, a straightforward approach is first of all, we just randomly start from a point, let's say here. Now, given here, then we calculate the gradient, right? We calculate the gradient of this point. And if the gradient is not zero, we can move to the next point based on the gradient. Okay. Then one of the optimality condition is when the gradient becomes zero, then the corresponding value will be the kind of minimum value. So here you can see for this red point, for this small region, at this point, the gradient will become zero. So if we just rely on this local search, we may probably stop here because intuitively we find the value, we find the point that gives us a zero gradient, right? However, if you start the search from here, right, following the same gradient descent process, you will converge to this solution, right? You may not go continue to the other regions. So if you start from here or here, you may still get this local optimal value here. But if you are lucky enough, you start from this part, now you will converge to the true and global optimal value. So you can see that for this complex problem, sometimes whether we are able to find the global optima depends on our starting point. So that is something you have to understand for local optima and the global optima. But of course, certainly, as I said, we want to find the global optima. So later on, I will introduce some criteria. We need to make sure that this problem is convex. And as long as it's convex, the local optima will be the global optima. Okay. Now we have talked about the orally how the optimization problem is, but mathematically how do we formulate them will be an important question. Okay, so generally speaking, for an optimization model, we have a objective function which is denoted as here fu, while f is our objective function and u is our decision variable. Okay, you can see here objective is to minimize this function f given the value of u, and certainly the value of u that can result in the minimum value of f is called a solution. Okay, and besides, sometimes for a mathematical model, we may have different kinds of constraints. Okay, the constraints generally can be divided into equality constraint and inequality constraint, denoted as G and H here. Apart from U, we also have X and Y, right? So to summarize, you can see f is objective function, the one you want to minimize, and the G and H are equality and inequality constraint, which means your problem has to satisfy within this G and H. So G and H will define the feasible region of the whole problem. And U is called optimization variable, which means you are going to search a value of U so that the F will be minimum. And this optimization variable is also called control variable or decision variable, because that means this variable is under your control, right? After you search U, you can set this U, then you will have a minimum value of F. And it's also called the decision variable because we are actually making decisions on U, okay, to minimize objective, okay. And x and y, okay, x is called a state variable, which is usually also called a dependent variable. So that means the value of this x will depend on u. This x is not directly controllable, but its value depends on the decision variable u. Remember in the energy internet lecture, I have introduced the microgrid operation problem, right? We divide the control variable and the state variable. Remember, for the microgrid case, the state variable is the branch power flow and the voltage magnitude. In other words, this branch power flow and the voltage magnitude, they are not directly controlled, right? We cannot set the branch power flow to be this value or that value. However, this branch power flow, the value depends on how we dispatch the generators, the energy storage systems. That's why this variable is called state or dependent variable. And last but not least, y is so-called parameters. I remember I have also introduced this in the energy internet session. The parameters is a kind of objectively given values which are out of your control. We cannot change it. For example, the line parameters, right, and the load demand, and the power output of the wind and the solar systems, right? So these values are totally out of our control. We can just take them as an input. And in practice, these parameters could be considered as either deterministic values or uncertain values. Deterministic values means that this value is a kind of deterministic and fixed. There is no uncertainty. Well, if we model this y as uncertain value, that means practically this value will have a kind of variation within a certain range. All this value will follow a probability distribution. Okay, so by modeling y to be either deterministic or uncertain, we will have different optimization solution algorithms. So later on, I will introduce a kind of a stochastic optimization approach, which can model y as uncertain parameters following a certain probability distribution. Okay, so that is something you have to well understand beforehand. Now, optimization, solution of the optimization. Okay, just now I have said the solution of the problem actually is the value set of u. Okay, here we can denote as u star. The vector of u star is called the optimal or solution of the problem, since it can achieve the smallest objective value among all the available or feasible vectors that satisfy the constraint. Okay, so mathematically we can denote this one if we have fu star. So value of fu star is always smaller or equal to fz, and z is any value within the feasible region defined by the equality constraint and the inequality constraint. Okay, so here is the so-called optimal solution of the model. Now, in terms of the model properties, basically we can classify the optimization model into a linear model or a nonlinear model. Okay. Now, linear model, you can see here, it will satisfy such property. Okay, this is our objective function f. So if we have f, a times u plus b times p, okay, both u and p are uh, decision variables. If this f equals to a times fu plus b times fp, then this problem is called a linear problem. Otherwise, all other problems which do not satisfy this property is called a nonlinear problem. Okay, so to be a linear problem, both the objective function and the constraint have to be linear. Okay, now this is the case. Okay, this is the case. We have 1, 2, 3, 4, 5. We actually have 5 constraints. All are linear. You can see. One is x1 formulated by x1 axis. The other is formulated by x2 axis. Okay, so here you can see that for x1, it has to be larger than 0. For s2, it also has to be larger than 0. On top of it, we have these 3 linear constraints, which will form a feasible region. Okay, feasible region. So this region is the kind of, they form up the region for the candidate solution, which means the solution must exist in this region. Okay, and this solution will lead to the smallest value of f. So this is a so-called linearity and nonlinearity. Okay. And another concept for mathematical optimization is the convexity. Okay, convex. Convex means the objective and the constraint have to satisfy this property. Okay, you can see once again f a times u plus b times p is smaller or equal to a times f plus b times fp. Okay, so clearly you can see that linear format, linear property is a special case of the convex property, right? Because linear means the left side equal to the right side, and the convex means the left side could be either smaller or equal to the right hand side. Okay. So if both objective and constraint can satisfy this property, we can call this optimization model as a convex. Otherwise, the problem will be considered as a non-convex problem. Okay. So strictly, simply speaking, convexity is more general than linearity. Now, let me show how can we understand the convexity. Okay, basically, if we have such a feasible region, okay, feasible region, for any 2 points within the region, let me change the point. Okay, so for any point within the region, the line connecting the 2 points is always within the region. Then this case is convex. Okay. Otherwise, for another kind of feasible region for 2 points, any 2 points, okay, for any 2 points, if for any 2 points, the connected line between the 2 points is outside of the feasible region, then this will be considered as a non-convex case. Okay, so you can see for the left-hand side, for any 2 points, as long as you can draw, they will always be within the feasible region, right? But for the right-hand side, you can see clearly we can find some examples cases where the connected line between the 2 points are outside of the feasible region. Okay, so the left side one is convex, right-hand side is non-convex. Okay. Now, so far, I suppose many participants are curious why convexity is so important. Now, let me show you again. Okay, let me still use the original example. Remember that, as I just briefly introduced, when we want to find a solution of optimization problem, we use the gradient, right? A quick approach is to use the gradient and follow the gradient to search the optimal value. But we have to start from a given certain point. Let's say if we start from here, we calculate the gradient. Clearly, the gradient is not zero, gradient is negative. Then following this gradient, we can calculate a new solution here. Then once again, we calculate the gradient again, and this gradient remains non-zero. So we continue this process until we find a zero gradient point here. Now here you can see we consider this is the solution. And for this special case, this quadratic feasible region, clearly you can see that this is a convex case, right? This is a convex because within the the feasible region, for any 2 points, you can not find a kind of line outside the region. Okay, so here you can see for this convex case, as long as you can find the optimal solution, it will be the global optimal solution, right? However, if the problem is not convex, like this, if this is a true the entire feasible region, and clearly you can see it's not convex. Why? Because because you can see clearly for any 2 points, if I connect it like this, you can see part of the line is outside the feasible region, right? Outside the feasible region. So for this case, it's a non-convex case. Now, as I said, depending on the starting point, we may converge or we may search the different optimal solution. If we still start from this point, we will get this red point. But if we start from this green point, we will find this solution. Now, clearly, this solution is better than the left-hand side. So this will be your global optimal, the green point. But this red point is the so-called local optima within this small feasible region. Okay. Now you can see here for the non-convex problem, we are unsure whether the found solution is global optimal or not. Not to mention the a further complex feasible region. If this is the entire feasible region, you can see that it looks more complex and clearly it's unconvex. It's not unconvex, right? Because clearly this part is outside the feasible region. Now, if we want to search the optimal solution for this problem, and if we start from here, and we can converge to this solution. And clearly you can see this solution is better than the green and the red point. And this is your global optimal. However, once again, you can see that whether we are able to find the global optima for this non-convex problem is uncertain, right? That really depends on, let me just cancel the drawings. That really depends on whether we are good enough, we are lucky enough to find a good starting point. Okay, but as long as the problem is convex, just as I shown for the first case, as long as we can find the solution, it will be the global optima. So the conclusion is here. For a convex problem, the local optima is also the global optima. But if it's not a convex problem, we are unsure on that. Okay, we are unsure on that. The whether it's global optima is not guaranteed. Okay, that's why convexity is so important. That's why in reality, we prefer convex problem. Okay, we prefer convex problem. Then I suppose some participant may wonder, okay, however, in practice, certainly most of the problems are extremely complex. They should not be convex, right? For this case, how can we do? Well, for this non-convex problem, we can try to do something. We can try to convex the problem, right? We can convex a non-convex problem to be a convex form. Just take this case as an example. If we know such a kind of feasible region, if we're able to connect this point to this point, if we're able to connect this point to this point, okay, then we redefine the new feasible region as this. Now you can see the whole problem like circled by this red line. You can see here becomes a convex problem. So no matter where we start our search, we will always converge to this solution. And this solution is clearly a global optima. So in mathematical optimization area, the convexation is one of the very effective and sometimes necessary step to do a problem modeling. Okay, even it's originally non-convex, we can still try to convexify the problem. Okay, so I have introduced some fundamentals of the mathematical programming. However, in order to solve the problem, there are numerous algorithms, for example, the simplex algorithm and other solution algorithm. Now, we don't have time to go through the detailed algorithm because, optimization itself is a separate subject and which requires a lot of time of teaching. But for power engineers, what we do is that we can utilize the commercial solvers which are available in the market. And there are also, open source free solvers to be used. So as an engineer, our focus is to model the power system problem into a standard optimization model. And after that, we can directly apply a solver to solve it. Okay, so my point is, as a power engineer, okay, we may not be strong enough in mathematics compared with mathematician, okay, but we can focus ourselves on problem modeling, okay, for either an economic dispatch problem, microgrid operation problem, or even microgrid planning problem. We can try to model them into a standard optimization format, just like what we have shown here. This could be a standard format. And as long as we formulate it, we can apply the existing solvers available in the market to solve it. But once again, we certainly need to model the problem as an easily trackable one. For example, it is linear, quadratic, and convex, because as I just explained, only the convex problem can guarantee you the global optima, right? So when we have a complex power system problem, we try to simplify it. We try to make a linear model. We try to make a convex model, okay? Now, for different types of the model, we have different solvers. Okay, most famous ones are Simplex, Groby, Mosaic. These three are, mostly widely used commercial solvers. But if you are a researcher or student, you can get a free license. You go to their website and request for free license. And if you are using MATLAB, MATLAB also has some solvers such as the Lean Pro. It is for linear programming. Okay, so it depends on the format of the model, being linear, quadratic, mixed integer linear, or mixed integer quadratic. We can use all these kinds of solvers. Okay, And for the mixed integer and the mixed quadratic, that means the problem, the decision variables contains both continuous variable and integer variable. Okay, integer variable, for example, could be 1 or 0, which denotes the on and off status of a unit, or it could be just a discrete number to denote the positions of the transformer type changer, okay, or the positions of the capacitor bank, right? So that's why we may also have mixed integer programming. And okay, for sometimes, no matter how much effort we put, the problem is always nonlinear. Okay, it's difficult to make a linear format. So if this is the case, we can still use this open source solver to solve this nonlinear problem. However, we cannot guarantee its optimality sometimes, and we cannot guarantee its solution time. Sometimes it may take extra long time to solve the model. And mixed integer nonlinear programming, very difficult to solve, and this open source solver can do it. However, once again, we cannot guarantee the performance and the solution time. And for the non-convex problem, yeah, we cannot guarantee the optimality. Okay, so most of the case, we wish our model could be formulated in these four formats: linear, quadratic, mixed integer linear, or mixed integer quadratic. Okay, and as long as you can do that, you can directly call for a solver to do it. And in terms of the programming platform, we can use MATLAB, and we can use Python, okay, nowadays. And there are separate professional optimization platforms, such as GAMS, Ample, okay. These two are kind of specialized programming platform for optimization. And the MATLAB, for MATLAB, there is a very good toolbox called YAMIP. Written in MATLAB, very easy to use. You can also go to the website to search this. YAMIP is kind of open source, free for download. Okay. All right, so that is about some fundamentals of the mathematical programming. Then after that, I will introduce the economic dispatch and the optimal power flow, which are two most basic tools for power system operation. Okay. Now, economic dispatch, here is the so-called problem description. Objective of the economic dispatch is to minimize the total cost of generation while supplying the load. So here you can see that we have the total load L, and we have three generators A, B, C. They are producing electricity, right? So our objective is to optimally determine the output of the three generators while minimizing their total cost, because each generators, they may have different cost item. For example, generator A may be a natural gas generator. Generator B might be a hydropower generator, and generator C may be a kind of a coal-fired generator. So their generation costs are different. Okay, then, however, they have to satisfy the total power demand, right? The total power output A, B, C will equal to L. So for mathematical modeling, we have an equality constraint. The load need equals to the total power generation. And besides, each generator certainly will have its upper and lower limit, right? Depending on their capacity. So we will also have inequality constraint. Now here you can see we can quickly formulate equality constraint and inequality constraint. This one denotes that the total power generation equals to the total load. And this one denotes that the generator has to satisfy its lower and the maximum capacity. Sometimes certainly the minimum value is 0, right? And the terms of the objective function, okay, sometimes we use this quadratic cost curve to denote the generation cost of the generator. So basically you can see that the generation cost of a generator I equals to coefficient AI times the square of the power output, and plus the coefficient bi times its power generation output, and plus a constant ci. So this is the total generation cost. Now here you can see that we have a kind of very compact, very simple mathematical model. Now, of course, the constraints are all linear, right? The constraints are all linear. Then how about the objective function? Objective function, since we have a quadratic item, so the objective function is a quadratic one, okay? And of course, quadratic one remains the convex. So the whole problem is a convex problem. Now as long as we can formulate this one in either MATLAB or Python, you can directly call for a solver to get the solution. So that is about the economic dispatch model. So economic dispatch, you can see very simple, very straightforward. So it's very basic. So it has a lot of limitations or inadequacies. Now, first one, you can see that the economic dispatch does not consider the network, right? We just consider the 3 generators supplying the load, but where is the network, the power grid? It is not considered. So the economic dispatch ignores the power flow model. Okay, and besides, you can see that since we only consider the real power, right? We don't consider the network. So where is the voltage? The voltage of different buses are not considered either. So the economic dispatch results, they may result in unacceptable power flows in the branch or unacceptable voltage magnitudes in the bus. So economic dispatch, I mean, in other words, they may not satisfy the operational limits of a practical power grid. Okay. Now, in order to cope with these inadequacies, later on, people have developed the optimal power flow technique, so-called OPF. Now, OPF is nowadays a widely applied tool for power system operation and market clearance. Okay. Now, by its name, optimal power flow is to optimize the entire power flow of the network. So similar to economic dispatch, for the objective function, we can minimize the total cost of the generation output. However, a very different constraint, very important difference comes from the equality constraint. Because, for the economic dispatch, we don't consider the power network, right? No power flow model is considered. But for OPF, okay, power flow equations are considered as the equality constraint. Okay, the power balanced, supply and demand is balanced and modeled by these power flow equations. And inequality constraint, similar to economic dispatch, right? The network, the operation limits, the line flow of different branches, the voltage magnitude of each buses, and the limit on the control variables, right? The upper bound and the lower bound of the generators and transformer, tap changers, capacitor banks. So all kinds of decision variables can be considered. Now, here, once again, here is a list of different kinds of decision variables. For example, we can dispatch the generator power output. We can dispatch the generator's voltage settings. Okay, we can dispatch the positions of the transformer taps and the position of the phase shifter taps, status of the capacitor banks on and off, right? And we can even optimize the power electronics devices. And besides, we can optimize the load shedding. Okay, if there is a need to shed the load, what will be the optimal amount to be shed, right? We can certainly optimize this. Then these control or decision variables are usually denoted as U, okay, as a vector of U. Now, state variables, we just go through the mathematical modeling. What will be the state variables for optimal power flow? Now, as I explained before, state variable is the value that cannot be directly controlled, but it depends on the decision variable. So in OPF problem, this state variable is the response of the system. in change of control variables, includes the magnitude of the voltage at each bus. Right? Imagine that practically we cannot directly control the voltage magnitude of each bus. Instead, we actually optimize the generator output or the transformer type changes to indirectly change the voltage magnitude. Okay, so that is the case. However, note that for generator bus we can change its voltage setting, right? And the angle of the voltage, right? This value certainly cannot be directly optimized either, right? We cannot change the phase angles of each bus, but except for slack bus, right? In power flow model slack bus, we have V and theta to be set. And then the power flows through each branch. This one is not directly controlled. Again, I just emphasized a lot of times for microgrid, right? When we optimize the operation, we cannot control how much power is from bus A to bus B. We cannot do that. We are actually indirectly determining the power flow based on our decision variables. And the reactive power output of the generator. Practically we are not directly control the reactive power output of the generator. What we do is actually to change the generator bus, the voltage setting. So indirectly, change its reactive power output. This is for the generator, so-called excitation control, right? And so these state variables are denoted as X, okay, as X. And the parameters, once again, parameters are known values of the system. They are objectively given. We cannot change it. So in practice, we have this network topology, network electrical parameters, generator cost functions, right? They are also objectively given. Generator limits, they are physical constraints that we cannot change and we can only satisfy. So all these parameters are denoted as y, okay, as a vector of y. Then objective functions, okay, traditionally we minimize the total generation cost. Similarly here, you can see we use these quadratic functions. But besides, the OPF can also model other control objective functions. For example, sometimes we want to minimize the change in the control variables, right? Originally, we have a status of the system operation status. Sometimes we want to change it, but we want to satisfy a constraint, but we want to minimize the change. Okay, so this is a new status, this is the original status, so we want to minimize the change. Okay, and besides, we can minimize the power system loss, power loss, and you can also minimize other objective functions as long as you want. Okay, but clearly you want to model the objective functions in a kind of simple way or kind of mathematically tractable way. However, the biggest challenge of the OPF come from the equality constraints. Remember, for OPF, we have to model the power flow equations of the network. Now, this is the power flow of the power grid, right? So for each bus, so for example, bus K, this is the total power balance. It equals to this formula, right? The bus power injection equals to the voltage times the conductance and also the cosine and sine of the angle difference. This is based on the Kirchhoff current law, right? So we can use this formula to model the power flow. Now look at the power flow equations. Since we have this multiplication, right, between different buses, and we have this cosine item, sine item. So clearly these power flow equations, they are nonlinear and non-convex, unfortunately, right? It's nonlinear and non-convex. So unfortunately, it's very difficult to solve the original optimal power flow model, right? Because it's non-convex. And even you find the solution, we cannot guarantee it is a true global solution. Inequality constraints, they are relatively simple. Limits on the control variables, operation limits of the branch flow, operation limits of the voltage magnitude. But most important thing is For a practical large-scale network, we may have high number of lines, hundreds of control variables, right? Sometimes we may have hundreds of the generators and transformer type changes and some others. So mathematically speaking, the problem size is very large, okay, a very large problem size. Okay, and very importantly, due to the power flow models, the problem is nonlinear and non-convex. Okay, and besides, some variables are discrete. For example, the positions of transformer, status of the capacitor. So the whole problem sometimes will be a mixed integer, non-convex programming, right? Mixed integer non-convex programming. Now, how can we solve it? So over the past, let's say maybe 40 years or even 50 years, numerous researchers have devoted their efforts into this OPF research. Nowadays, the most kind of widely used solution algorithm is the interior point method. Okay, interior point method. It can relatively have a high performance in terms of the solution quality and the solution speed. So if you're interested, you go to some, you can directly search interior point method. There is kind of a lot of tutorials behind that. But once again, as I just said, as a power engineer, right, sometimes we just focus on modeling. And the solution algorithm are already developed by mathematicians. Okay, and even for OPF, there is a very famous open source package in MATLAB called MATPower. Okay, this one is developed by a set of researchers in Cornell University. So you can go to the website and download a copy of MATPower. So the MATPower can do both power flow study and also optimal power flow study. Okay, you can directly solve OPF in this toolbox. Okay, in this toolbox. So that is, the second part, the economic dispatch and optimal power flow. Now, before we move to the third part, the microgrid operation, let's have a 5 minutes break. Okay, 5 minutes break. Please come back in 5 minutes. All right. All right. Hello again. Let's go back to the third part, the optimal operation of the microgrid. So I will focus on two subtopics. One is on the energy management of the microgrid with energy storage system. Secondly is the voltage regulation of the microgrid. Okay. Both of them are actually formulated as the optimization model. Okay, so first of all, let's have a recap of the microgrid. Although I have introduced this concept since the second lecture, right? In the Energy Internet, we have introduced that, but officially, we have some definitions for the microgrid. You can see here we have several different definitions from the US DOE, the working group in SIGRI, and also a textbook from Professor Nichols, a very top expert in microgrid. So if you read these definitions, you will find that the microgrid definitions, they are more or less the same, okay, more or less similar. Basically, the microgrid, first of all, should be a low voltage distribution grid. Secondly, this grid should contain flexible loads and demand distributed energy resources. Okay, you can see demand DER, distributed, including distributed generators, storage device, or controllable loads. Okay. And thirdly, the whole grid system, whole system could operate in a controlled, coordinated way, either with either in the grid connecting mode or the disconnected mode. Okay. So to summarize, microgrids, number one, low voltage distribution network. Secondly, you have DER, distributed energy resources. Number three, the whole microgrid system can operate as an individual and controllable entity. Okay, so that the microgrid, they can like coordinate or the interact with the main grid. Remember, in one of our demonstration projects in Singapore, I have introduced how the microgrid can support or provide the ancillary service to the main grid. Okay, now in order to operate or dispatch the microgrid, we have to model it. All right, so first of all, I mean, the objective function and the constraints, they are relatively easy, but the challenge usually come from the power flow model. But for the distribution network, unlike the meshed high voltage network, the distribution grid usually is in a radial structure. So this power flow could be easier to model. Okay, if we have like this example, we have a radial structured distribution grid. This is a let's say, grid substation. And from here, we have this distribution network. You can see it's a tree structured, radial tree structured. So according to KCL, Kirchhoff current law, we can formulate the power injection equals to the total power output of a bus, right? So for each power injection, you can see that this is the input and this is the output, and also output, and also the power loss. Okay, power loss is always in the transmission lines. So we use this I square times R to denote the power loss. This is for real power, for reactive power, and for voltage. Okay, for voltage, according to the voltage drop equation, we can formulate it here. Okay, and then for the total power load, you can see we have this net load for each bus. Note that here, sometimes we may have, I mean, distributed generation, right? So we have P load and PG. PG denote P generation. So we can use this equation set to denote the power flow of the distribution network instead of the full power flow model we just shown in previous slides. However, even for this distribution power flow model, you can see it is still a non-convex and nonlinear, especially because of these items. Okay, because of these items. Now, remember what I have said. Our focus should try to linearize or convexify the original model, right? So to do that, we can do some processing. Okay, we can first of all we can ignore this power loss. Since the power loss during the power loss in the distribution grid might not be so big compared with the the load demand. So sometimes we can temporarily ignore the power loss so that you can see the two equations of P and Q becomes much simpler, right? Because we have ignored this power loss temporarily. And for the voltage, okay, voltage is more complex, but we can still linearize it into this form. And this form, remember yesterday I have briefly introduced, this is delta V, right? This is this okay, I can't this is delta V, okay, this is delta V, which depends on P times R plus Q times X, okay, X. So you can see that we can just set this V as a Vs. Okay, Vs is a fixed value. Because it's a main substation, we can just take it as 1.0 per unit. So now you can see the voltage also becomes linear, right? This is linear, this is also linear, and all the remaining are linear as well. And for the voltage, if we have the tap change ratio, okay, defined by tap, you can see this is also a linear. And last but not least, since we ignore the power loss initially, wait a second, I have to. Since the void, since we have ignored the power loss during the calculation, we have to recalculate the power loss in the end. Okay, so you can see we still calculate the power loss using the calculated PI and QI as well as the VS. Now, in such a way, the original nonlinear non-convex model is become linear and the convex model, right? So with that, we are able to further formulate the operation problem model. Okay, now for energy management, this slide I have introduced before in the energy internet session. We have different control variables, state variables, and the parameters. Right. Then our objective is to optimize the microgrid by dispatching these controllable sources. Okay. Now here, let me just show you a realistic example in our research lab. We have formed up a hybrid energy storage system using a supercapacitor bank, you can see here, as well as a lead acid battery. Okay. So this, as we have introduced yesterday for energy storage technologies, supercapacitor, it has a very high power density, but the energy density is low because it's expensive and difficult to be scaled up, right? And the lead acid battery, by contrast, has a relatively high energy density, right? It's cheaper and I mean, it's more mature, but its power density compared with supercapacitor is smaller, right? Supercap has extremely fast responding speed because the electrons are directly stored in the capacitors. Now, by forming up this hybrid energy storage system, we can utilize the advantages. We can use the high power density from supercapacitor and the high energy density from the battery. Okay. Then we have such a microgrid which contains hybrid ESS. We have renewable energy resources, PV and wind turbine, and we have the total load. Okay, we have the total load. Our objective is to dispatch the hybrid ESS with interactions with the main grid. Okay, because within this microgrid, we have renewables, we have hybrid ESS, we are selling power to the load. But in the meantime, we may also import or export the power to the utility grid. So our objective function is to minimize the total operation cost or maximize the total operation revenue of the microgrid system. And here we have to consider the operation cost of the battery because, you know, yesterday we also discussed that during the charging and discharging, the battery capacity will degrade, right? Because certain chemical reactions will happen and it will increase the internal resistance of the battery, and in the end, the available capacity will be smaller. So during each charging discharging event, the certain capacity will lose. So we want to model this problem. And according to some studies, the degradation of the battery capacity mainly depends on the depth of discharge. Okay, depth of discharge means how deep the battery is discharged from one level to another level of state of charge. So basically, if you discharge the battery too deep, it will accelerate the aging of the battery. Now, this curve shows the relationship between the depth of discharge and the number of available life cycles. Now, clearly you can see that when you have a high depth of discharge, the available number of life cycles is dramatically, exponentially decreased. Okay, so we want to model this operation cost into our microgrid dispatch problem. So here we formulate the problem model. Okay, we want to minimize the total operation cost minus the revenue. Okay, so the cost come from the hybrid ESS and also come from the power purchased from the main grid. And the revenue is the power that we sell to our customer, our loads. Okay, and the constraints include the power balance, right, between the total generation locally and the power imported from the main grid. They must equal to the total power demand. And the network power flow and the voltage constraints are denoted as the linearized distribution power flow model. And we have, of course, the constraints, including the diesel generators capacity constraint. Here, actually, we can also consider the diesel generator. You remember in our microgrid project, we have a Rolls-Royce diesel genset. So we need to model the upper and the lower capacity bound. And for the energy storage system, the state of the charge, right, should be considered. And if we have electrical vehicles, we can also consider their charging and discharging time. Okay, so they will be equations can be more detailed. Okay, can be more detailed. You can refer to this paper to see the more details. And then the whole problem in the end is formulated as a mixed integer linear programming, okay, MILP model. And this model can be directly solved by a lot of available solvers. So here you can see for mixed integer linear programming, we have at least 3 commercial solvers to do. So in our research, we use Groby to solve the whole model, and the model can be quickly solved. Okay. Now let me show some results. Okay, so here you can see that you remember what I have said. I want to make use of the high power density of the capacitor, a supercapacitor, and the high energy density of the battery. So these two, energy storage technologies, they compensate with each other. The battery has a relatively slow responding speed. So we dispatch it in the first stage. Okay, we dispatch every hour. Okay, every hour. And the supercapacitor is much faster. So we dispatch it every 1 minute. Every 1 minute. So you can see that we have these two operational time intervals or stages. For the first stage, we dispatch the batteries. Okay, every hour we determine the output of the battery. While within every hour, for each minute in the hour, we dispatch the supercapacitor, and the two, stages are coordinated so that battery can provide, longer power charging discharging because it's high energy density, while supercapacitor provide faster but shorter power charging discharging within each operation interval. Okay. Now here, let me show you some dispatch results. We actually consider the electricity price, the dynamic electricity price, because in the end, we want to buy cheap electricity and then sell to our customers. So you can see here, the electricity price is shown in the blue dashed line. So you can see over a day, over 24 hours, it always varying. And okay, now we have a supercapacitor and the battery. You can see these are their power charging discharging. This PCC means the power exchange between the microgrid and the main grid. So you can see that during the low electricity price, we try to import power from the main grid, right, by charging the supercapacitor and the battery. So you can see that their power are charged. And during the high electricity price period, we will discharge our supercapacitor and a battery to the customers so that we don't need to buy electricity. And sometimes we even sell the electricity back to the main grid. So you can see here during this period, when the price is high, we are actually export the power back to the grid through this point of coupling. And you can see that the battery and the supercapacitor, they are discharging, right? They're discharging. And this is another example. You can see during this high electricity price period, the battery is actually discharging, exporting power back to the grid, okay, back to the grid. Okay, so in the meantime, for different period, you can see the energy storage systems, they are kind of optimally charged and discharged. Now, in terms of their SOC, so you can see for the state of charge of the battery and the supercapacitor, they are in different ranges of different operation hours. So here we actually consider the different penetration of the energy storage system. We consider 10% penetration, 20, 30, and even 40. Okay, so you can see if you look at the battery, okay, for different penetrations, it does not has too much difference, okay, because the battery mainly is to store bulk energy during the low electricity price and sell the power back to the grid. But for the supercapacitor, you can see the state of charge change more significantly than the battery because the supercapacitor's responding speed is faster, right? That's why we want to dispatch it more frequently. So you can see that compared with battery, its SOC is more variable. However, you can see under different penetration levels, 10 to 40, the supercapacitors SOC change are also different. So the conclusion is that for this microgrid operation with the main grid for power exchange, the different penetration of supercapacitor and battery are different, especially for the supercapacitor, certainly higher penetration, higher capacity of the supercapacitor will be more helpful, While for the energy, for the battery, it is not that, the difference is not that apparent, okay? Now, after that, I want to explain a kind of stochastic optimization approach to solve the uncertainty. Remember, we have emphasized a lot of times for the optimization model, the parameters could be modeled as deterministic or uncertain. While in realistic settings, the wind and solar power certainly are uncertain, right? We cannot accurately predict them. Although we predict them, they will vary within a certain range, okay? So we can model the power output of the wind or solar in a probability distribution manner, okay? So for this example, the wind speed can be modeled as a Weibull distribution, right? Here you can see this is a Weibull distribution under different, this is a histogram graph of the wind speed under different speed level, the frequency, and also the probability are different, okay? So most of the case, you can see that the wind speed is around 7 to 9 meter per second, okay? Now, question is, how can we model this uncertain parameter into an optimization model? So we can apply the stochastic optimization approach. So basically, for the objective function f, we have u as the decision variable, we have this x as a dependent variable, and we have this as a uncertain parameter. Now, instead of minimizing the single objective value, we are actually minimizing the expectation value of the f, because now with the uncertain variable, uncertain parameter here, the value of f could be could have multiple cases, multiple so-called scenarios. So we are aiming, we will minimize the expect of the different scenarios of the value, okay? So you can see the objective function becomes the E expectation of f. And as I said, this uncertain parameter will follow a probability distribution, right? Its value and its probability of occurrence. Now, In order to solve this model, we can sample the different values of this uncertain parameter within this probability density function. Now, for each scenario, we can sample a value, right? If we can sample a key, total of key different scenarios, and then each scenario will have a corresponding probability from the probability density function. So in the end, we can convert this expectation value function into this format. Okay, so E now equals to what? Equals to the probability times the corresponding value function under the random scenario. Okay, under the random scenario. So you can see now the objective function still becomes a fixed one, becomes a deterministic one. So by doing that, the stochastic problem is converted to be a deterministic problem model. So it can be solved as usual. So that's how we can model the uncertain parameters into the optimization problem using this probability distribution-based or scenario-based modeling. Okay, so that is how we can address the uncertainty in the microgrid operation. Now, after that, the voltage regulation. Okay, voltage certainly is also an important parameter, technical parameter in the power network. So how can we control the power, the voltage? We remember that the voltage is not directly controlled because essentially they are state variables. What we can do is to control the reactive power sources, including the capacitor banks, the transformer tap changes, as well as the inverters of the solar PV system. This one I have introduced a lot of times because inverters, they are power electronic device. They can absorb, they can produce reactive power. So if they are dispatchable, we can certainly support the network's voltage regulation. So here, this is an example of the distribution network. We have a solar PV, right? Each solar PV certainly has a inverter. And then we have capacitor bank. Capacitor bank also produce reactive power. So our objective is to dispatch PV inverters, capacitor banks, as well as the tap changers of the transformer to satisfy the bus voltage. But for voltage regulation, what will be our objective function? Yeah, certainly we can try to minimize the total voltage deviation, or we maximize the voltage performance. But in practice, sometimes we want to minimize the total power loss because the reactive power will cause power loss as well. By optimizing the reactive power output, we can minimize the total power loss in the network. So voltage regulation usually has this power loss objective function. So this is objective function. Then in terms of the constraints, we have a power balance. Once again, similar to the original operation problem, the total demand equals to the total distributed generation plus the total power import from the main grid. And the network power flow model, we use the linearized distribution flow equations. And the constraints, constraints for inverters, we need to be careful. Inverters originally are designed to convert the real power from DC to AC. So it has a parent capacity S. And during the PV inverter PV panel generation, certain capacity of the inverter are used for converting the real power generation from the PV panels. So the remaining capacity within the S will be used for reactive power support. So the available reactive power capacity equals to this one. It has to be smaller or equal to this one. So this is a constraint that we need to be careful. But clearly, this is a non-linear, non-convex one. So we can just simplify it. We can set a proper ratio. Let's say we only use 10% of S for voltage regulation, right? This is possible in practice. And for the capacitor bank's capacity, yes, it has a lower and upper bound for its rating. And the capacitor tap change ratios, yes, we have minimal and maximal positions, mixed positions. So in this case, the whole problem will be modeled as a mixed integer quadratic problem. Now, why is a quadratic? It's because the power loss. Okay, the power loss function in the end, remember we have just introduced. You can see that the power loss is modeled here. This is clearly a quadratic function. So in the end, this voltage regulation problem will be a MIQP. Okay, and MIQP can be solved by either simplex or Groby. Okay, so that is how we address this problem. Now let me show you some simulation results. Once again, we dispatch the power converters and we dispatch the capacitor banks. Our objective is to minimize the power loss, right? Capacitor banks here, and this is transformer tap changes. So you can see that for 24 hours, right? For 24 hours, this is the power output of the converters. And this is the positions of the OLTCs. And this is the output of the capacitor banks. And this is the corresponding power loss of a day. Okay, power loss of a day. It already minimized. Okay. So more technical details are provided in this paper. Okay, this paper is also highly cited by many times, more than 300 times. So if you are interested, you can take a look of this paper. And okay, actually, for my research group, we have been working on microgrid for more than 10 years, covering the control, operation, and the planning of the microgrid. So here I just list our publication list for you to refer. If you are interested, you can see here, these references, they are actually for control. Because of the time limitation in this lecture, I didn't cover control because it's more complex. But if you're interested, you can refer these references. We have control papers, and this one is for the control everything, and this one is for the planning. You can see deployment of energy storage system. This is a planning paper. This is control and optimization. This is also energy management paper, and we even have we have this control as well, a different control method, and also operation for multi-energy microgrid, considering uncertainties, and for multi-energy microgrid in both grid connected mode and islanded mode. Yeah, we have mathematical models for them. And what else? Even for the nano grid, right? Smarter buildings, we also have this work, and this work is a joint work between myself and my visitors from IIT Delhi. Okay, back to 2019. At that time, I have visited IIT Delhi for a week. After that, we have completed this joint work, and students visited my group for 1 year. Yeah, so that is, my collaboration with our India colleagues before. And besides this optimal planning of distributed generators in microgrids, and also distributed control. This is the one I just explained, the voltage regulation, okay, and also the energy dispatch, right? The frequency control, okay, using the energy storage system. Yesterday I have introduced how can we use energy storage system for frequency control. Yeah. And in terms of the algorithms, we also have developed algorithms, voltage regulation, everything. Yeah, we have covered. So we actually have summarized our research in microgrid in this textbook. Okay, this one, you can see the title, Coordination of Distributed Energy Resources in Microgrid, covering the optimization, the control, as well as the hardware in the loop validation. Okay, so this again course, Professor Kumar has already taught you about the property simulation. So in this book, we have also covered this context. If you're interested, you can go to this website to take a further look at this book. Okay, that is the end of the lecture slides. Then we still have several minutes for Q&A. Yeah, please let me know if you have any questions. Any questions, please?
Professor, have one question.
Yes.
The optimization function which has been used is a nonlinear, is it? In all the
Yeah.
cases, most of the cases.
Yes. So that depends on what type of the objective functions are you considering. So for this one, the power loss, you can see for distribution network, we can make it a quadratic format. So this one will become a quadratic programming. And for this cost, right, it sometimes can be modeled as a linear format. So that could be linear. But sometimes if the cost function is too complex, it has to be nonlinear, non-convex. And we need to find some ways to either linearize it or simplify it. Yeah. So that really depends.
I mean, these optimization studies which we are going to do in the smart grid or in the microgrid, we are going to do in the offline study only, everything.
Yes, yes.
So there is no point of any time like in the real time applications where you optimize it and then you start generating the power or you start connecting the distributed generation, right? It's not
Yeah.
like that.
Yeah. So the microgrid as a whole, they can support the main grid's operation by providing ancillary service. Remember, in the Energy Internet, when I introduced the REITs project in Singapore, the final objective is to connect the grid system to the main grid, then participate in the electricity market. Yeah. Okay, a student asked me, can we access data from the set? I don't. You can check the website. Personally, I didn't try, but I suppose some data could be accessible. Yeah, you go to that website, and there is a kind of contact email. You can check with them. Yeah. Yeah. Any like further questions? All
Any
right.
questions?
If no more questions, I think this afternoon, what will be the remaining schedule? I think this afternoon there will be a.
The valedictory is there, Professor, at
Okay, yeah.
5 p.m. Singapore time.
Okay, yes, the feedback session, yes. Yeah, you will also have after that, you will have another
Session. Yeah, power quality
session in the
issues.
power quality issues, and followed by examination. Then I will have a feedback with you. Okay.
Yeah.
Okay, so I wish one more question. Delivery and Suffer. Okay. Yeah, thank you. Thank you. I hope you have enjoyed the whole lecture. Yes. Okay, I will meet you in the afternoon after you finish the examination. Okay.
Yeah.
Good luck.
Yeah. Thank you.
Yeah.
Thank you,
Bye
Professor.
bye.
Bye bye.
Bye.
Just a minute. Let's stop recording.